Close your eyes and imagine the night sky. Stars scatter across the darkness like diamonds on black velvet. Each point of light tells a story of nuclear fire burning millions of miles away. But tonight, we're not looking at the stars themselves. We're looking at the spaces between them. In those dark regions, something extraordinary hides. Something so mysterious that it bends the very fabric of space around it. Something that pulls with such incredible force that even light, the fastest thing in the universe, cannot escape its grasp. You might think of empty space as nothing at all. A void. A blank canvas waiting to be filled. But space is alive with invisible forces. It curves and stretches like a rubber sheet. It carries waves of gravity that ripple outward from massive objects. And in some places, space curves so sharply that it forms a well with no bottom. These are black holes. The universe's greatest mystery and perhaps its most beautiful creation. The name black hole sounds frightening. It conjures images of cosmic monsters devouring everything in their path. But this fear comes from not understanding what they truly are. Black holes are not evil creatures lurking in space. They are simply places where gravity has become so strong that it creates something entirely new. Think of gravity as the universe's way of bringing things together. Your feet stay planted on Earth because gravity pulls you downward. The moon orbits our planet because Earth's gravity holds it close. Our entire solar system dances around the sun, held in place by the star's gravitational embrace. Now imagine gravity growing stronger and stronger. Not the gentle pull that keeps you grounded, but a force so intense that it warps everything around it. This is what happens when massive stars reach the end of their lives and collapse into themselves. But we're getting ahead of ourselves. Before we explore how black holes form, let's understand what makes them so special. What makes them different from ordinary objects in space? The secret lies in something called the event horizon. This invisible boundary surrounds every black hole like a one-way door. You can pass through it, but you can never return. From the outside, this boundary looks like empty space. There's no wall, no barrier you can touch. It's simply the point where gravity becomes so strong that nothing can escape. Imagine standing at the edge of a waterfall. The water flows peacefully until it reaches the edge, then plunges down with unstoppable force. The event horizon is like that edge, but for space itself. Cross it, and you begin an irreversible journey inward. This might sound terrifying, but there's beauty in this cosmic boundary. It represents the ultimate limit of our physical universe. A place where the normal rules of physics stretch and change. Where time slows to a crawl and space curves back on itself. Scientists have been fascinated by black holes for over a century. When Albert Einstein first wrote his equations describing gravity, he didn't expect them to predict such strange objects. But the mathematics pointed toward something extraordinary. Places where matter could collapse so completely that it creates a region of infinite density surrounded by empty space. For decades, black holes existed only in theory. Scientists could calculate their properties and predict their behavior, but no one had ever seen one. They were invisible by definition, trapping light that would normally reveal their presence to our telescopes. Then something remarkable happened. Scientists learned to look for black holes by watching how they affect their surroundings. Like invisible dancers moving through a crowded room, black holes reveal themselves by the way they push and pull on nearby matter. When gas and dust spiral toward a black hole, they heat up from friction and compression. This material glows brilliantly before disappearing forever beyond the event horizon. These glowing disks, called accretion disks, became the first signs that black holes truly exist. Today, we've detected thousands of black holes throughout our galaxy and beyond. Some are stellar mass black holes, formed when individual stars collapse. Others are supermassive giants, millions of times heavier than our Sun, lurking at the centers of galaxies. Each black hole is unique, yet they all share certain fundamental properties. They have mass, which determines the strength of their gravitational pull. They may spin, rotating like cosmic tops at incredible speeds. And they have that mysterious event horizon, marking the point of no return. But black holes are not permanent fixtures in the universe. They can grow by consuming matter that falls into them. They can merge with other black holes, creating gravitational waves that ripple through spacetime itself. And according to our best theories, they can even evaporate over unimaginably long periods, slowly releasing their energy back into the cosmos. This evaporation process, first described by physicist Stephen Hawking, suggests that black holes are not truly black. They emit a faint radiation, so weak that it would take longer than the age of the universe to detect from any known black hole. Yet this radiation hints at deep connections between gravity, quantum mechanics, and the nature of information itself. As you drift toward sleep tonight, let your mind wander to these cosmic mysteries. Black holes exist at the intersection of the known and unknown. They are laboratories where the universe tests its most fundamental laws. They are poems written in the language of mathematics, describing realities beyond our everyday experience. The darkness between the stars is not empty. It holds secrets that challenge our understanding of space, time, and reality itself. In this darkness, gravity performs its most dramatic dance, creating objects so strange that they seem like science fiction, yet so real that their influence shapes the evolution of entire galaxies. Tomorrow's journey will take us deeper into this mystery. We'll witness the spectacular death of a massive star, and see how that final moment of collapse creates something that will endure for billions of years. We'll discover how giants fall, and in their falling, create doorways to the unknown. Picture a star so massive that it makes our sun look like a grain of sand beside a boulder. This giant burns with the fury of a million suns, pouring light and energy into the cosmos at a rate that seems impossible. Yet for all its power and brightness, this stellar giant is racing toward its own destruction. Stars are born from clouds of gas and dust floating in the darkness of space. Gravity slowly pulls these particles together, creating a growing ball of matter. As more material gathers, the pressure at the center grows stronger. Temperature rises. Eventually, the core becomes so hot and dense that hydrogen atoms begin to fuse together, creating helium and releasing tremendous amounts of energy. This is how a star lights up. Nuclear fusion in its heart creates the light that travels across billions of miles to reach your eyes. The star becomes a perfect balance between two opposing forces. Gravity pulls inward, trying to crush everything into a single point. The energy from fusion pushes outward, fighting against gravity's embrace. For most stars, this balance lasts for billions of years. Our sun has been burning steadily for over 4 billion years and will continue for another 5 billion. It lives a long, peaceful life, slowly converting hydrogen into helium, warming the planets that orbit around it. But massive stars live fast and die young. A star 20 times heavier than our sun burns through its fuel at an incredible rate. While our sun will shine for 10 billion years, these giants exhaust their nuclear fuel in just a few million years. They live like candles in a hurricane, burning bright and beautiful, but destined to burn out quickly. As the giant star ages, something remarkable happens in its core. The hydrogen fuel begins to run low. The nuclear fires that have burned for millions of years start to dim. Without the outward pressure from fusion, gravity begins to win the ancient battle. The star's core starts to contract. As it shrinks, it heats up again. This heat allows heavier elements to fuse together. Helium atoms combine to create carbon. Carbon fuses into oxygen. Oxygen becomes silicon. Each new fusion reaction releases energy, but less than the one before. The star becomes like a cosmic onion, with different elements burning in layers throughout its interior. In the very center, the heaviest elements form. Around that core, lighter elements continue their own fusion reactions. The star swells to enormous size, becoming what astronomers call a supergiant. But this layered burning cannot continue forever. Eventually, the star tries to fuse iron in its core. Iron is special among the elements. When lighter elements fuse together, they release energy. When iron tries to fuse into heavier elements, it actually absorbs energy instead of releasing it. This is the beginning of the end. Iron fusion steals energy from the star's core instead of providing it. The nuclear fires that have supported the star for millions of years suddenly go out. Without this energy pushing outward, gravity wins completely and catastrophically. What happens next occurs faster than you can blink. The star's core, now made mostly of iron, collapses under its own weight. Material that once filled a space larger than Earth crashes inward and compresses into a ball just a few miles across. This collapse happens in less than a second. The core becomes so dense that a teaspoon of its matter would weigh as much as a mountain. Electrons and protons are crushed together so tightly that they merge into neutrons. The core bounces back from this incredible compression, sending a shock wave racing outward through the star. This shock wave tears through the star's outer layers, heating them to billions of degrees. The star explodes in what astronomers call a supernova. For a few weeks, this single dying star can shine brighter than an entire galaxy containing billions of other stars. The explosion scatters most of the star's material into space. Elements forged in the star's core during millions of years of fusion are thrown across the cosmos. The carbon in your body, the oxygen you breathe, the iron in your blood, all of these elements were created in the heart of a dying star and scattered by its final explosion. But not everything escapes. The star's core, now compressed beyond imagination, may survive the explosion. If the original star was massive enough, this core becomes something extraordinary. It becomes a black hole. The collapsed core contains more mass than our entire sun, crushed into a space smaller than a city. Its gravity is so intense that it warps space and time around itself. Nothing that falls toward this remnant can ever escape. Not matter, not light, not even information about what falls in. This transformation from star to black hole happens in moments. Millions of years of steady burning end in a spectacular explosion that creates one of the universe's most mysterious objects. The star that once lit up its corner of space becomes a region where light itself cannot exist. Yet there is beauty in this cosmic death. The supernova explosion enriches space with heavy elements, providing the raw materials for new stars, planets, and eventually life itself. The black hole that remains becomes a gravitational anchor, helping to shape the structure of its galaxy for billions of years to come. Not every massive star becomes a black hole. Stars that are very large, but not quite large enough, may collapse into neutron stars instead. These incredibly dense objects are made entirely of neutrons, packed so tightly that they spin hundreds of times per second, sweeping beams of radio waves across space like cosmic lighthouses. The boundary between neutron star formation and black hole formation is still being studied by scientists. It depends on the exact mass of the collapsing core and the details of how matter behaves under such extreme conditions. As you rest tonight, consider the magnificent violence and beauty of stellar death. Every atom in your body except hydrogen was forged in the nuclear furnace of a star. You are literally made of stardust, connected to the cosmos in the most fundamental way possible. The giants that fall in spectacular supernovas give birth to black holes, but they also give birth to the elements that make life possible. In their dying moments, they ensure that the universe becomes more complex and beautiful. Soon, we will cross the threshold that these stellar deaths create, and explore the mysterious boundary where space and time themselves begin to bend in impossible ways. Imagine walking through a forest on a misty morning. You move forward through the gentle fog, and suddenly you realize you've crossed from shadow into sunlight. There was no wall, no fence, no sign to mark the change. Yet something fundamental shifted around you. The air feels different. The light has changed. You've crossed an invisible boundary. This is what the event horizon feels like. Not a barrier you can touch or see, but a threshold that changes everything. It surrounds every black hole like an invisible sphere, marking the point where the normal rules of space and time begin to bend and stretch in extraordinary ways. The named event horizon comes from the idea that it marks the limit of events you can observe from the outside world. Beyond this boundary, no information can ever travel back to tell you what happens next. It's like standing at the edge of a vast ocean, knowing that messages thrown into the water will never wash back to shore. But what makes this boundary so special? Why does crossing an invisible line in empty space change everything so dramatically? The answer lies in understanding how gravity affects the very fabric of space and time. Einstein showed us that space and time are not separate things, but parts of a single entity called spacetime. Imagine spacetime as a soft rubber sheet stretched tight. When you place a heavy ball on the sheet, it creates a depression. Smaller objects rolled nearby will curve toward the ball, following the bent shape of the sheet. This is how gravity works. Massive objects bend spacetime around them, and other objects follow these curves. The Earth curves spacetime just enough to keep you firmly planted on the ground. The Sun's curve is strong enough to hold all the planets in their orbits. A black hole bends spacetime so extremely that it creates something like a deep well with infinitely steep sides. The event horizon marks the edge of this well, the point where the curve becomes so sharp that nothing can climb back out. From far away, the event horizon looks perfectly smooth and featureless. There are no warning signs, no visible changes in the space around it. If you could somehow approach a black hole in a spaceship, you would see empty space right up until the moment you crossed the boundary. Only then would you realize that you had passed the point of no return. The size of the event horizon depends entirely on the mass of the black hole. A black hole with the same mass as our Sun would have an event horizon about 4 miles across. A supermassive black hole at the center of a galaxy might have an event horizon larger than our entire solar system. But here's something beautiful about event horizons: they grow smoothly as black holes gain mass. When matter falls into a black hole, the event horizon expands gently outward to accommodate the additional mass. It's like watching a soap bubble grow larger as you blow more air into it. Time behaves strangely near the event horizon. As you fall toward a black hole, time passes normally for you. Your watch ticks at its usual rate. Your heartbeat maintains its steady rhythm. But to someone watching from far away, your time appears to slow down dramatically. This effect becomes more pronounced as you approach the event horizon. To the distant observer, you seem to move slower and slower, like a movie played in extreme slow motion. At the exact moment you cross the event horizon, you appear to freeze completely, suspended at the boundary forever. But this is just an illusion created by the strange behavior of time near black holes. From your perspective, you cross the event horizon smoothly and continue falling inward. The boundary passes around you like morning mist, invisible and intangible. Light behaves strangely near the event horizon too. Photons of light that try to escape from just inside the boundary find themselves trapped, circling the black hole in tight orbits. This creates a sphere of trapped light called the photon sphere, located just outside the event horizon. Some light manages to escape from very close to the event horizon, but it pays a price. The light loses energy as it climbs out of the black hole's gravitational well, becoming redshifted. This means that bright white light emitted near the event horizon appears dim and red by the time it reaches distant observers. These effects create a kind of shadow around every black hole. The event horizon itself is invisible, but the region around it appears dark because so little light can escape from nearby. This shadow is what scientists photographed in the famous images of black holes captured by the Event Horizon Telescope. The event horizon also marks an information boundary. In our everyday world, information can always be recovered in principle. Burn a book, and the information isn't truly lost, it's just scrambled into the patterns of smoke and ash. But information that crosses an event horizon seems to disappear from our universe completely. This creates one of the biggest puzzles in modern physics. Quantum mechanics says that information can never be truly destroyed. But general relativity says that anything crossing an event horizon is gone forever. These two fundamental theories of physics seem to contradict each other at the event horizon. Scientists call this the information paradox, and it remains one of the deepest unsolved mysteries in science. Some theorists suggest that information is somehow encoded on the surface of the event horizon itself, like a hologram that contains all the information about what has fallen inside. Others propose that black holes eventually evaporate completely through a process called Hawking radiation, somehow releasing all the information they've consumed back into the universe. But this process would take longer than the current age of the universe for any known black hole. The event horizon represents both an ending and a beginning. It marks the end of your ability to send messages back to the outside universe. But it also marks the beginning of a journey into the most extreme environment that physics allows. As you drift toward sleep, let your mind rest at this cosmic threshold. The event horizon whispers of mysteries that lie beyond the reach of ordinary experience. It speaks of places where space and time dance to rhythms we're only beginning to understand. Tomorrow, we'll cross this invisible boundary together and discover what waits on the other side, where the gentle pull of gravity becomes something altogether more intimate and strange. Close your eyes and imagine yourself floating peacefully in the darkness of space, approaching a black hole. You drift slowly inward, past the event horizon, continuing your journey toward the center. At first, nothing seems different. Your body feels normal. Your breathing remains steady. But gradually, something extraordinary begins to happen. You start to notice that your feet feel heavier than your head. This difference is so slight at first that you might think you're imagining it. But as you continue falling, the sensation grows stronger. Your feet are being pulled more forcefully than the rest of your body. This is the beginning of what scientists call tidal forces. The name comes from the same effect that creates ocean tides on Earth. The moon's gravity pulls more strongly on the side of Earth closest to it, and less strongly on the far side. This difference in gravitational pull creates the rhythm of high and low tides that has marked the passage of time for billions of years. Around a black hole, these tidal forces become much more dramatic. The gravity at your feet, which are closer to the black hole center, is significantly stronger than the gravity at your head. This difference stretches your body gently at first, then more insistently as you fall deeper. Scientists have given this stretching process a playful name, spaghettification. Like pasta being pulled into long, thin strands, your body would slowly elongate as the tidal forces work on you. It sounds frightening when described quickly, but the actual process would be surprisingly gentle and gradual. Think of yourself as a piece of soft clay being shaped by invisible hands. The forces work slowly, stretching you longer and thinner with each passing moment. Your feet drift farther ahead of your head. Your arms and legs begin to extend. You become taller and narrower, like your reflection in a funhouse mirror. The speed of this stretching depends entirely on the size of the black hole. Around a supermassive black hole, the kind found at the center of galaxies, the tidal forces are surprisingly gentle. These giants are so large that their gravity changes very gradually with distance. You could cross the event horizon and fall for hours before noticing any stretching at all. But around smaller black holes, the ones formed from collapsed stars, tidal forces are much stronger. The gravity changes rapidly over short distances, creating intense stretching that would reshape your body quickly and dramatically. Imagine the difference between walking down a gentle hillside versus stepping off a steep cliff. Both involve moving downward, but the rate of change creates completely different experiences. Supermassive black holes are like gentle hills of gravity. Stellar mass black holes are like gravity cliffs. The stretching affects more than just your body. If you carried a rigid object with you, like a metal rod, it would stretch too. The end closer to the black hole would be pulled more strongly, while the far end would lag behind. Eventually, even the strongest materials would be pulled apart by these relentless tidal forces. But there's something beautiful about this process. It represents gravity at its most artistic, sculpting matter according to the fundamental geometry of spacetime. The same force that holds planets in their orbits and keeps your feet on the ground becomes a cosmic sculptor, reshaping everything according to its own perfect mathematical laws. As you stretch, you also fall faster and faster toward the black hole center. The point at the very heart of the black hole, called the singularity, represents the ultimate destination of your journey. Here, according to our current understanding of physics, the curvature of spacetime becomes infinite. Density becomes infinite. The normal rules of space and time break down completely. But you would never actually reach the singularity intact. Long before arriving at that mysterious point, the tidal forces would have stretched you beyond recognition. Your atoms would be pulled apart and scattered, joining the stream of matter spiraling inward. This might sound like a violent end, but there's a strange poetry to it. You would become part of something larger than yourself. Your atoms, forged in the heart of ancient stars, would join the black hole's growing mass. In a sense, you would become one with this most extreme object in the universe. The tidal forces also affect time itself. As you stretch and fall, your personal experience of time continues normally. Seconds tick by at their usual rate. But to an outside observer, your time appears to slow dramatically. The closer you get to the singularity, the slower your time appears to pass. This creates a strange paradox. From your perspective, the journey to the center takes a finite amount of time. But from the outside universe's perspective, you appear to freeze at the event horizon, your image redshifted and dimmed until it fades from view. Scientists still debate what really happens during this final phase of the journey. Some theories suggest that the stretching process might be modified by quantum effects near the singularity. Others propose that the information contained in your atoms might somehow be preserved and encoded on the black hole's surface. These questions remain at the frontier of physics, where our current theories reach their limits. But there's comfort in knowing that even in this most extreme environment, the universe follows consistent mathematical laws. Gravity may stretch and reshape matter, but it does so according to precise, beautiful equations. As you rest tonight, consider the elegant way that gravity shapes everything around us. From the gentle curve of Earth's surface to the dramatic stretching near black holes, the same fundamental force creates order and beauty throughout the cosmos. Tomorrow, we'll explore how this stretching dance affects the passage of time itself, and discover why moments near a black hole can stretch as thin as golden honey in the morning sun. Imagine time as a river flowing at different speeds. In the gentle streams of everyday life, seconds tick by at their familiar pace. Your heartbeat marks a steady rhythm. Clocks on the wall keep perfect time with one another. But as you approach a black hole, this river of time begins to slow and deepen in the most extraordinary way. You float peacefully near the event horizon, unaware that something profound is happening to time itself around you. Your watch continues ticking at its normal rate. Your breath flows in and out with its usual rhythm. From your perspective, nothing has changed. But if someone could observe you from far away, they would witness something magical. To that distant observer, your movements begin to slow down like a movie played in slow motion. Your gestures become languid and dreamlike. The second hand on your watch appears to crawl around the face with increasing sluggishness. You seem to be moving through invisible honey that grows thicker and thicker. This is time dilation, one of Einstein's most beautiful discoveries. Time is not the constant, universal rhythm we once believed it to be. Instead, it flows at different rates depending on how strong gravity is around you. The stronger the gravitational field, the slower time passes relative to regions where gravity is weaker. Think of time as a soft fabric that can be stretched and compressed. On Earth, this fabric is barely affected by our planet's gentle gravity. The difference in time's flow between your head and your feet is so small that it would take millions of years to notice even a tiny change. But near a black hole, gravity becomes so intense that it stretches the fabric of time dramatically. Each second of your experience near the event horizon corresponds to many seconds in the outside universe. As you get closer to the black hole, this effect becomes more and more pronounced. The mathematics behind this are precise and beautiful. If you could hover just outside the event horizon of a black hole, 1 hour of your time might equal several years in the rest of the universe. Return to Earth after such a journey, and you would find that decades had passed while you experienced only a brief visit to the edge of forever. This isn't science fiction or philosophical speculation. It's a real physical effect that has been measured and confirmed countless times. Atomic clocks flown on airplanes run slightly faster than identical clocks left on the ground, because they experience slightly weaker gravity at high altitude. GPS satellites must constantly adjust their clocks to account for time dilation, or they would lose accuracy within hours. Near a black hole, these effects become extreme. The gravitational time dilation grows stronger and stronger as you approach the event horizon. At the exact boundary itself, time dilation becomes infinite. From the outside universe's perspective, you would appear to freeze completely at that invisible threshold. But here's the beautiful paradox: you never feel this slowing down. Your personal experience of time remains perfectly normal. Your heartbeat keeps its steady rhythm. Your thoughts flow at their usual pace. The second hand on your watch continues its familiar circle. You are always in sync with your own local time, no matter how slowly that time appears to pass to distant observers. This creates a strange kind of cosmic loneliness. As you drift closer to the black hole, you become increasingly disconnected from the time flow of the rest of the universe. Messages sent from Earth take longer and longer to reach you, and your replies back to them become increasingly redshifted and faint. Imagine trying to have a conversation with someone far from the black hole. You speak a sentence that takes 5 seconds in your personal time. But by the time those words travel back to the distant observer, they might have waited hours or days to hear your complete thought. The conversation stretches across vast differences in the flow of time itself. Light itself participates in this cosmic dance. Photons climbing out of the black hole's gravitational well lose energy in the process, becoming redshifted. A bright white flashlight beam emitted near the event horizon would appear dim and red to someone watching from far away. The light carries the signature of time dilation in its changing color. This redshifting becomes more extreme as the light source gets closer to the event horizon. Eventually, the light becomes so redshifted that it fades beyond the ability of any instrument to detect. The source appears to dim and vanish, frozen at the moment it crossed the event horizon. Yet from your perspective falling into the black hole, you see something completely different. The light around you maintains its normal color and brightness. The stars above you continue to shine with their familiar hues. It's only when you look back toward the outside universe that you notice something strange happening. The universe behind you appears to speed up. Stars that normally take millions of years to evolve seem to change and age in fast forward. If you could somehow maintain your position near the event horizon for what feels like a few hours, you might watch the entire future history of the universe play out behind you in accelerated time. This creates a kind of time machine effect. By approaching a black hole and then escaping back to normal space, you could theoretically travel into the future. The stronger the gravitational field you visit, the farther into the future you would emerge when you return. But this time travel only works in one direction. You cannot use gravitational time dilation to visit the past. Time's arrow still points forward, even when that arrow moves at different speeds in different places. The slowing of time near black holes has inspired countless stories and films, but the reality is more subtle and beautiful than most fiction suggests. It's not a violent wrenching of time, but a gentle, mathematical stretching that follows precise laws of physics. Scientists have used these time dilation effects to study black holes from a distance. By watching how light changes as it escapes from near the event horizon, they can map the gravitational field and understand the black hole's properties without ever getting close to the dangerous regions near the center. As you prepare for sleep tonight, let your mind rest in this gentle flow of time. Every moment of your life unfolds at exactly the right pace for your experience. Whether time flows quickly or slowly, your consciousness moves through it at the perfect rhythm for your journey. Tomorrow, we'll explore one of the deepest mysteries that emerges from this dance with time: what happens to information, to memories, to the very essence of what makes you unique when it encounters the ultimate boundary where even light cannot return. Picture yourself sitting by a warm fireplace, watching the flames dance and flicker. You toss a handwritten letter into the fire and watch it burn. The paper crumbles into ash. The ink disappears in smoke. But even though the letter is gone, the information it contained isn't truly lost forever. In principle, if you could track every molecule of smoke, every particle of ash, every photon of light released by the flames, you could reconstruct what the letter said. The information has been scrambled and scattered, but it still exists somewhere in the pattern of the fire's remains. This is one of the fundamental principles of physics. Information can be transformed, hidden, or spread out, but it can never be completely destroyed. Like energy, information is conserved throughout the universe. It changes form, but it never simply vanishes into nothingness. But black holes seem to challenge this sacred rule. When something crosses the event horizon, it disappears from our universe completely. No signal, no light, no information can ever return to tell us what happened. The black hole appears to erase whatever falls into it from the pages of reality itself. This creates what scientists call the information paradox. It's one of the most profound puzzles in modern physics, sitting at the boundary between Einstein's theory of gravity and the quantum mechanics that governs the smallest particles of matter. Imagine you're holding a book filled with your most precious memories. Your first day of school. The sound of your grandmother's voice. The feeling of summer rain on your skin. Every detail of your life is written in this book, encoded in the patterns of ink on paper. Now imagine dropping this book into a black hole. According to Einstein's equations, the book crosses the event horizon and continues falling toward the center. From your perspective outside, the book appears to freeze at the boundary, its image growing dimmer and redder until it fades from view completely. But what happens to all that information? All those memories, experiences, and details that made the book unique? Do they simply cease to exist when they cross the event horizon? Or do they continue to exist somewhere beyond our ability to observe them? For decades, most physicists believed that the information was simply lost. Black holes seem to be the universe's ultimate shredding machines, capable of erasing anything that fell into them. The information paradox was seen as an unfortunate but unavoidable consequence of how gravity works in extreme conditions. But then Stephen Hawking made a discovery that changed everything. He realized that black holes aren't completely black. They emit a faint radiation that slowly causes them to evaporate over incredibly long periods of time. This Hawking radiation carries energy away from the black hole, gradually reducing its mass until it disappears completely. At first, this seemed to make the information paradox even worse. Hawking's calculations suggested that the radiation escaping from black holes was completely random, containing no trace of the information that had fallen in. If this were true, then when a black hole finally evaporated, all the information it had consumed would be lost forever. This possibility deeply troubled physicists. It would mean that the universe could genuinely forget things, that information could be permanently erased from reality. It would require rewriting some of the most fundamental laws of physics. But Hawking's discovery also opened new possibilities. If black holes could evaporate completely through radiation, perhaps they somehow encoded all the information they had consumed in that escaping radiation. Maybe the information wasn't lost after all, just transformed in ways we didn't yet understand. Think of it like a cosmic library that appears to burn down completely. At first, it seems like all the books are lost forever. But imagine if the smoke from the fire somehow contained the text of every book, written in a code so complex that it would take eons to decipher. The information would still exist, just in a form almost impossible to read. Some scientists proposed that the information might be stored on the surface of the event horizon itself, like a hologram that contains a complete record of everything that has ever fallen in. According to this idea, the three-dimensional reality inside the black hole might be entirely encoded in patterns on the two-dimensional surface of the event horizon. This holographic principle has become one of the most intriguing ideas in modern physics. It suggests that what we think of as the solid, three-dimensional world might actually be information stored on distant surfaces, like shadows cast by a more fundamental reality. Other theorists suggested that the information might escape through quantum entanglement, a mysterious connection that can exist between particles separated by vast distances. Perhaps the particles of Hawking radiation remain connected to the particles that fell into the black hole, carrying information out through these ghostly quantum links. The debate raged for decades, with brilliant minds proposing increasingly exotic solutions. Some suggested that black holes might not have event horizons at all, but instead be surrounded by firewalls of high-energy particles. Others proposed that the information might escape through microscopic wormholes connecting the black hole's interior to distant regions of space. Recently, many physicists have begun to believe that information is indeed preserved, though the mechanism remains mysterious. The consensus is shifting toward the idea that the information does escape, encoded in the Hawking radiation in incredibly subtle ways that would require vast computational power to decode. But this creates its own puzzles. If the information escapes encoded in the radiation, when does it start coming out? Does it begin escaping immediately, or only when the black hole is nearly evaporated? How can information about things that fell in recently escape before the black hole has had time to process it? These questions push us to the very limits of our understanding of space, time, and reality itself. They force us to consider whether the familiar concepts of inside and outside, before and after, even have meaning in the extreme environment near a black hole. The information paradox remains unsolved, a beautiful mystery that sits at the heart of our quest to understand the universe. It reminds us that even in our age of scientific achievement, the cosmos still holds secrets that challenge our deepest assumptions about how reality works. As you prepare for sleep tonight, consider your own information. Your memories, your thoughts, your dreams are all patterns of information stored in the neural networks of your brain. Every experience you've had has left traces in the complex web of connections between your neurons. In sleep, your brain processes this information in mysterious ways, consolidating memories, exploring new connections, and sometimes creating the strange narratives we call dreams. Perhaps your sleeping mind engages in its own version of the information paradox, transforming the data of your daily experience into forms that transcend ordinary understanding. Tomorrow, we'll explore how black holes themselves might dream, radiating whispers of energy into the cosmic void in ways that challenge everything we thought we knew about emptiness and light. Imagine the quietest place you can think of. Perhaps a snow-covered forest on a windless night, where even your breath seems too loud. Or maybe the deep ocean floor, where darkness and silence reign supreme. But even in these peaceful places, there is always some gentle activity. Snow crystals shift slightly. Water molecules vibrate with thermal energy. True emptiness doesn't exist anywhere in nature. The same is true for the space around black holes. What appears to be the ultimate void, the darkest darkness, actually glows with the faintest possible light. This gentle radiation, so weak it would take billions of years to warm a cup of tea, represents one of the most beautiful discoveries in modern physics. Stephen Hawking first glimpsed this phenomenon while thinking about the strange behavior of empty space itself. What we call empty space isn't truly empty at all. It's filled with quantum fluctuations, tiny energy variations that pop in and out of existence faster than anything can measure them. Think of the vacuum of space as a calm lake that looks perfectly still from a distance. But if you could examine the surface closely enough, you would see tiny ripples and waves constantly appearing and disappearing. These quantum fluctuations are like microscopic waves on the surface of reality itself. Normally, these fluctuations balance out perfectly. A tiny amount of positive energy appears, matched instantly by an equal amount of negative energy. They exist for the briefest possible moment, then cancel each other out and disappear. The net effect is zero, leaving space seemingly empty and quiet. But near a black hole's event horizon, something remarkable happens to this delicate dance. The extreme curvature of spacetime tears apart some of these quantum pairs before they can annihilate each other. One particle from the pair falls into the black hole, while its partner escapes into space as real radiation. This escaping radiation is what we call Hawking radiation. It emerges from the quantum foam near the event horizon like steam rising from a barely warm cup of tea. The radiation is so faint that it's colder than the cosmic background radiation left over from the Big Bang. Yet it's real, and it has profound implications for our understanding of black holes. The temperature of this radiation depends on the size of the black hole in a beautifully inverse way. Smaller black holes are hotter. Larger black holes are cooler. A black hole with the mass of our Sun would have a temperature of about 6/millionths of a degree above absolute zero. That's incredibly cold, far colder than the space around it. Supermassive black holes, the giants that lurk at the centers of galaxies, are even colder. Their Hawking radiation has a temperature so low that it's almost meaningless to measure. These cosmic giants radiate so weakly that they would take longer than the current age of the universe to lose even a tiny fraction of their mass. But here's where the story becomes even more intriguing. As a black hole radiates energy away, it slowly loses mass. And as it loses mass, it gets smaller. As it gets smaller, it gets hotter. As it gets hotter, it radiates energy away faster. The process accelerates like a cosmic snowball rolling downhill. This means that black holes are not eternal. Given enough time, even the most massive black hole will eventually evaporate completely through Hawking radiation. The universe's ultimate symbols of permanence are actually temporary, though their lifespans stretch across time periods so vast they dwarf the current age of the cosmos. The radiation itself carries a strange kind of poetry. It emerges from the boundary between existence and non-existence, born from the quantum uncertainty that underlies all reality. Each photon of Hawking radiation represents a victory of something over nothing, a tiny escape from the ultimate prison. Yet this radiation appears to be completely random, carrying no information about what has fallen into the black hole. It's like cosmic static, white noise radiating uniformly in all directions. This randomness is what creates the information paradox we explored earlier. How can the black hole erase all traces of what it has consumed? Some physicists believe that the randomness is only apparent. They propose that the radiation does carry information, but encoded in correlation so subtle that they would require extraordinary computational power to detect. The information might be there, hidden in the quantum relationships between different particles of radiation. Others suggest that the information doesn't emerge in the radiation at all, but remains somehow encoded on the event horizon itself. According to this view, the surface of a black hole acts like a cosmic hard drive, storing perfect records of everything that has ever fallen in. The process of Hawking radiation also creates another beautiful phenomenon. As particle pairs are separated near the event horizon, the particles that fall in have negative energy from the black hole's perspective. This negative energy reduces the black hole's mass, while the positive energy particles that escape carry that lost mass away into space. It's as if the black hole pays for each escaping particle by giving up a tiny bit of itself. The universe maintains perfect accounting, ensuring that energy is never created or destroyed, only transferred from one form to another. This radiation also connects black holes to thermodynamics, the science of heat and energy. Black holes have temperature, just like any hot object. They have entropy, a measure of disorder, proportional to the area of their event horizons. They follow the same fundamental laws that govern steam engines and melting ice cubes. The connection between black holes and thermodynamics suggests deep relationships between gravity, quantum mechanics, and information theory. These connections hint at a more unified understanding of physics, where the behavior of the largest objects in the universe emerges from the same principles that govern the smallest particles. As Hawking radiation slowly carries energy away from black holes, it also carries time. The evaporation process marks a kind of cosmic clock, measuring the passage of eons through the gentle glow of quantum light. Even in the darkest corners of the universe, time continues its forward march, counted in photons too faint to see. The discovery of Hawking radiation transformed our understanding of black holes from simple gravitational traps into complex thermodynamic systems that obey quantum laws. They are not just holes in space, but dynamic objects that interact with their environment in subtle and beautiful ways. Tonight, as you rest in the darkness of your room, remember that even the deepest darkness glows with invisible light. Quantum fluctuations dance around you, creating and destroying virtual particles in an endless ballet of energy and possibility. Tomorrow, we'll explore how this gentle radiation might carry the deepest secrets of reality itself, encoded on surfaces that exist at the very boundary between the known and unknowable. Hold your hand up toward a lamp and watch your shadow dance on the wall. The shadow looks flat, a simple silhouette with no depth or detail. Yet somehow, in that two-dimensional projection, you can recognize the shape of your fingers, the curve of your palm, the gesture you're making. The shadow contains information about the three-dimensional reality of your hand, encoded in a simpler form. Now imagine something far more extraordinary. What if the shadow contained not just the shape of your hand, but every detail of your entire being? Your memories, your thoughts, the pattern of every atom in your body. What if everything that makes you who you are could be perfectly encoded on that flat surface on the wall? This is the beautiful and mysterious idea behind the holographic principle, one of the most profound concepts to emerge from the study of black holes. It suggests that all the information in a three-dimensional region of space might be completely encoded on its two-dimensional boundary, like an impossibly complex shadow that contains more information than seems possible. The idea first arose from thinking about black holes and the information paradox. If information that falls into a black hole is somehow preserved, where could it possibly be stored? The interior of the black hole seems inaccessible to the outside universe. But perhaps the information never really goes inside at all. Picture the event horizon as a vast, invisible movie screen surrounding the black hole. According to the holographic principle, everything that appears to fall through this screen might actually be encoded on its surface, like actors whose three-dimensional performance is captured in a two-dimensional film. From the outside, you would see objects approaching the event horizon, slowing down due to time dilation, and eventually appearing to freeze at the boundary. Their images become dimmer and redder, but they never quite disappear. In the holographic view, this isn't just an optical illusion. The information about those objects really is stored on the event horizon surface. Think of a hologram you might see on a credit card or in a museum. When you look at it from different angles, you see different views of a three-dimensional object, even though the hologram itself is completely flat. All the information needed to reconstruct the three-dimensional image is encoded in the patterns of light and dark on the two-dimensional surface. The holographic principle suggests that reality itself might work this way. The rich, complex three-dimensional world we experience might be encoded on distant two-dimensional surfaces in ways we don't yet understand. We might all be shadows of information stored on boundaries we cannot see or touch. This idea transforms how we think about black holes. Instead of being holes in space that swallow information forever, they become cosmic information storage systems. Every bit of data about everything that has ever approached them gets written onto their event horizons in patterns too complex for us to read. The surface area of the event horizon determines how much information can be stored there. As more matter falls in, the black hole gains mass and its event horizon grows larger, providing more storage space for the additional information. The universe maintains perfect bookkeeping, never losing track of anything that has ever existed. But the holographic principle extends far beyond black holes. Some physicists believe it applies to the entire universe. According to this view, everything we see and experience in our three-dimensional cosmos might be encoded on a two-dimensional surface at the edge of the observable universe. Imagine the universe as a vast sphere, with everything we know and love happening inside. The holographic principle suggests that all this interior complexity might be nothing more than shadows cast by information stored on the sphere's surface. We would be like characters in an incredibly sophisticated movie, unaware that our entire reality is projected from a cosmic screen. This doesn't mean our experiences aren't real. The holographic encoding would be so perfect that the three-dimensional world it creates would be indistinguishable from fundamental reality. Your thoughts, feelings, and sensations would be just as genuine whether they arise from three-dimensional matter or from information encoded on a distant surface. The holographic principle also offers new perspectives on the nature of space itself. If all the information in a volume can be encoded on its boundary, then perhaps the interior volume isn't fundamental at all. Space might be emergent, arising from the complex relationships between bits of information stored on surfaces. This idea connects to quantum entanglement, the mysterious phenomenon where particles can remain connected across vast distances. Perhaps the entanglement between different regions of information on holographic surfaces creates the illusion of three-dimensional space, like a cosmic magic trick performed by quantum mechanics. Scientists have found evidence for holographic behavior in laboratory experiments with certain materials. Under specific conditions, the physics of these materials can be perfectly described by equations that live on their boundaries, even when the interesting phenomena happen in their interiors. String theory, one of physics' most ambitious attempts to unify all fundamental forces, naturally incorporates holographic principles. In string theory's mathematical framework, the holographic encoding of information emerges automatically from the theory's geometric structure. The holographic principle also suggests new ways to think about consciousness and identity. If your entire being can be encoded on a two-dimensional surface, what does that mean for your sense of existing in three-dimensional space? Are you the hologram, or are you the information that creates the hologram? These questions push us to the very edges of physics and philosophy. They ask us to consider whether the familiar concepts of inside and outside, here and there, even have fundamental meaning. Perhaps reality is more like a dream than we ever imagined, projected from sources we cannot directly perceive. As you settle into sleep tonight, let your mind rest with this beautiful possibility. Your dreams tonight might be holographic projections from the surface of your consciousness, encoding the full richness of your inner world in patterns that dance across the boundaries of sleep and waking. Tomorrow, we'll explore another way that black holes might connect distant regions of space and time, creating bridges that stretch across the cosmos in ways that challenge our understanding of distance itself. Imagine walking through a quiet park and discovering a tunnel beneath a hill. You enter one end surrounded by oak trees and morning mist, walk for just a few minutes through the gentle darkness, and emerge on the other side to find palm trees and ocean waves. The tunnel has somehow connected two places that should be thousands of miles apart. This is the dream of wormholes, cosmic tunnels that might connect distant regions of space and time through shortcuts hidden in the fabric of reality itself. They capture our imagination because they offer the possibility of traveling vast distances in impossibly short times, turning the universe into a more intimate and accessible place. The mathematical possibility of wormholes emerges naturally from Einstein's equations describing gravity and space-time. These equations don't just allow for the bending of space around massive objects like stars and planets. They also permit more exotic geometries, including bridges that connect different regions of the cosmos. Picture spacetime as a vast sheet of rubber stretched tight. We've seen how massive objects create depressions in this sheet, and how these depressions become the deep wells we call black holes. But the mathematics also allows for something more intriguing: tunnels that pass through the sheet itself, connecting distant points through pathways hidden in higher dimensions. The simplest wormhole connects two black holes to each other. Imagine two funnels placed mouth to mouth, creating a passage that goes down through one funnel and up through the other. Matter falling into the first black hole might theoretically emerge from the second one, having traveled through a hidden corridor in space-time. This kind of wormhole is called an Einstein-Rosen bridge, named after the physicists who first described it mathematically. The bridge would be incredibly short, perhaps just a few miles long, even if it connected black holes separated by billions of light-years in ordinary space. It would be the universe's ultimate shortcut. But there's a beautiful and frustrating problem with these natural wormholes. They appear to be fundamentally unstable. Like a soap bubble that pops the moment you touch it, a wormhole would collapse almost instantly, closing the bridge between its two ends before anything could pass through. The collapse happens because wormholes are sensitive to the slightest disturbance. Even a single photon of light trying to pass through would cause the tunnel to pinch shut. The walls of the wormhole would rush together faster than light itself, sealing the passage permanently and turning both ends into separate black holes. This instability isn't a minor engineering problem that might be solved with better technology. It's built into the fundamental structure of spacetime itself. General relativity allows wormholes to exist, but it also ensures they cannot persist long enough to be useful for travel. However, some physicists have proposed ways around this limitation. They suggest that wormholes might be kept open using exotic matter with negative energy density. This strange substance would push outward instead of pulling inward, counteracting the tendency of the wormhole to collapse. Think of negative energy as antigravity material that repels rather than attracts. A thin shell of this exotic matter lining the walls of a wormhole might keep the tunnel open indefinitely, creating a stable bridge between distant regions of space. But exotic matter with the required properties has never been observed in nature. While quantum mechanics suggests that such matter might be possible in principle, creating enough of it to stabilize a wormhole would require technology far beyond anything we can currently imagine. Even if stable wormholes could exist, they would create profound paradoxes if they allowed travel backward in time. Imagine a wormhole that connects two points not just in space, but also in time. You could enter the wormhole today and emerge yesterday, potentially meeting your younger self or changing events that have already happened. These time travel scenarios lead to logical contradictions that make physicists uncomfortable. Could you prevent your own birth by traveling back in time? Could you create information from nothing by sending yourself a message from the future? The mathematics of wormholes allows these possibilities, but they violate our understanding of causality. Some scientists propose that the universe has built-in protection against such paradoxes. Perhaps the laws of physics automatically prevent any wormhole configuration that would allow backward time travel. Or maybe the quantum fluctuations near a wormhole's mouth would become so intense that they would destroy anything trying to pass through. There's also the question of what travel through a wormhole would actually feel like. Unlike the dramatic stretching that occurs near black holes, passage through a wormhole might be surprisingly gentle. You would enter at one end moving at normal speed and emerge at the other end still moving at normal speed, having experienced nothing more dramatic than a brief journey through a tunnel. The walls of the wormhole would curve away from you as you pass through, creating a tube of spacetime that looks much like any other tunnel. You might see the opening at the far end growing larger as you approached, eventually emerging into a completely different region of the universe. But the view looking back might be extraordinary. Through the wormhole's mouth, you would see the region of space you had just left, possibly many billions of light-years away. The two ends of the wormhole would act like cosmic windows, allowing you to observe distant parts of the universe as if they were right next door. Some theoretical physicists have suggested that wormholes might occur naturally at the quantum level, constantly forming and disappearing in the foam of spacetime at the smallest scales. These tiny tunnels would be far too small for anything to pass through, but they might play a role in the fundamental structure of reality itself. Others have proposed that advanced civilizations might someday learn to create and stabilize their own wormholes, using them to build a transportation network that spans the galaxy. These artificial wormholes would require mastery of exotic physics and engineering on cosmic scales, but they're not definitively ruled out by known laws of nature. The search for naturally occurring wormholes continues through astronomical observations. Scientists look for gravitational lensing effects that might reveal the presence of wormhole mouths, or for other signatures that could distinguish wormholes from ordinary black holes. So far, no convincing evidence for wormholes has been found. Every object that initially appeared to be a wormhole has turned out to be something more conventional upon closer examination. The universe seems content to keep its shortcuts hidden, if they exist at all. The dream of wormholes reflects our deep desire to make the vast universe more navigable and connected. In a cosmos where the nearest star takes thousands of human lifetimes to reach, wormholes would transform space travel from an impossibility into an adventure. But perhaps the real beauty of wormholes lies not in their practical applications, but in what they teach us about the flexibility of spacetime itself. They show us that the universe is far stranger and more malleable than our everyday experience suggests, even if we can never actually use that strangeness to our advantage. Tonight, as you prepare for sleep, let your mind wander through the theoretical tunnels that mathematics has carved through the cosmos, knowing that even impossible dreams can teach us something profound about the nature of reality. Tomorrow, we'll return from these speculative journeys to consider what black holes ultimately are, neither pure destruction nor magical gateways, but something more subtle and beautiful than either extreme suggests. You've journeyed with me through the cosmic darkness, exploring the most mysterious objects in the universe. We've watched giant stars collapse into impossible densities. We've crossed invisible boundaries where time slows to a whisper. We've considered paradoxes that challenge our deepest understanding of reality itself. Now, as our exploration draws to a gentle close, we return to the question that began our journey together. Are black holes gateways or dead ends? The answer, like many profound truths, is both simpler and more complex than it first appears. Think of a river flowing toward a waterfall. The water rushes forward with increasing speed, following the inevitable pull of gravity. At the edge, it plunges over the cliff and disappears from view. To someone standing safely on the shore, the waterfall seems like an ending. The water that goes over never returns. It vanishes into the mist and spray below. But we know the story doesn't truly end there. The water continues its journey, flowing through hidden channels, eventually finding its way to the sea. What appears to be an ending from one perspective is simply a transformation from another. The water changes form, changes direction, but it never stops being water. Black holes are like cosmic waterfalls in the river of spacetime. Matter and energy flow toward them with increasing inevitability, eventually crossing the event horizon and disappearing from our view. From our perspective in the outside universe, this seems like the ultimate ending. Nothing that falls in ever returns to tell us what happens next. Yet through our journey together, we've discovered that the story is far more nuanced. Black holes are not simple destroyers, swallowing everything without trace. They are complex systems that obey precise physical laws, interacting with their environment in subtle and beautiful ways. They shape the galaxies around them, providing gravitational anchors that help organize matter on the largest scales. They regulate star formation in their vicinity, sometimes triggering the birth of new stars, sometimes preventing it. They grow and evolve over cosmic time, changing the structure of space itself as they acquire new mass. Through Hawking radiation, black holes slowly return their energy to the universe, though in forms so transformed that we can barely recognize the connection to what originally fell in. They participate in the cosmic dance of thermodynamics, having temperature and entropy like any other physical system. The information they consume may not be truly lost, but preserved in ways we're only beginning to understand. Whether encoded on their surfaces like cosmic holograms, or released through quantum correlations in their radiation, the essence of what enters a black hole may find ways to persist and eventually escape. In this sense, black holes are indeed gateways, though not the kind that science fiction often imagines. They are not portals to distant galaxies or pathways to parallel universes. Instead, they are gateways to deeper understanding of the fundamental nature of reality itself. They force us to confront the limits of our familiar concepts of space and time. They reveal connections between gravity, quantum mechanics, and information theory that we never suspected. They show us that the universe is stranger, more interconnected, and more beautiful than we ever dared to imagine. Black holes also serve as gateways to humility. They remind us how much we still don't know about the cosmos we inhabit. Despite centuries of scientific progress, despite our sophisticated mathematics and powerful telescopes, these objects continue to surprise us with new puzzles and paradoxes. The very existence of black holes challenges us to expand our thinking beyond the comfortable boundaries of everyday experience. They ask us to consider what happens when space curves back on itself, when time stretches toward infinity, when information seems to disappear from the universe entirely. Yet in another sense, black holes are indeed dead ends, though not in the way we might fear. They represent the final state of gravitational collapse, the ultimate victory of gravity over all other forces. Once formed, they can only grow or slowly evaporate. They cannot be undone or reversed. The matter that forms them can never return to its original state. But even this finality has its own beauty. Black holes show us that the universe has absolute limits, boundaries beyond which certain kinds of information cannot pass. They create regions that are fundamentally disconnected from our experience, cosmic privacy zones where the normal rules of observation break down. This limitation is not a failure of the universe, but a feature. It preserves causality by ensuring that events inside black holes cannot influence events outside in ways that would create paradoxes. It maintains the consistency of physical law even in the most extreme environments. As you prepare for sleep tonight, consider how your own journey into dreams mirrors some aspects of approaching a black hole. You cross an invisible threshold into a realm where normal rules don't apply. Time flows differently in dreams. Space can fold and bend in impossible ways. Past, present, and future can exist simultaneously. Like information crossing an event horizon, your waking consciousness seems to disappear when you fall asleep. Yet something of you persists in the dream state, transformed but still recognizably you. Your memories, experiences, and personality continue to exist, though in forms that often seem strange and disconnected from waking logic. When you awaken, you carry traces of the dream world back with you, though the memories often fade quickly like Hawking radiation dissipating into the cosmic background. Sometimes the dreams leave lasting impacts, changing your thoughts or emotions in subtle ways that persist long after the dream itself is forgotten. The boundary between sleeping and waking, like the event horizon of a black hole, is both absolute and invisible. You cannot observe the exact moment of falling asleep from the inside. It happens gradually, then suddenly, like crossing into a region where different physical laws apply. Perhaps consciousness itself has event horizons, boundaries beyond which certain kinds of experience cannot be shared or communicated. Your inner life remains fundamentally private, accessible only to you, just as the interior of a black hole remains accessible only to what falls inside. The question of whether black holes are gateways or dead ends ultimately depends on your perspective and time scale. On human timescales, they appear to be final destinations, cosmic points of no return. But on the vast timescales of cosmology, they may be temporary way stations in the universe's ongoing evolution. They concentrate matter and energy in ways that may seed the formation of new structures. They may play crucial roles in the life cycles of galaxies. They may even, through mechanisms we don't yet understand, participate in the birth of new universes or new phases of cosmic evolution. The beauty of black holes lies not in resolving the tension between gateway and dead end, but in embodying both possibilities simultaneously. They are Schrödinger's cosmic objects, existing in a superposition of interpretations until we develop the theoretical tools to collapse that superposition into a single, clear understanding. But perhaps that moment of resolution will never come. Perhaps the ambiguity is fundamental, reflecting deep truths about the nature of knowledge and observation in a universe that remains mysteriously larger than our ability to comprehend it completely. Tonight, as sleep's own event horizon approaches, let your mind rest in the comfortable uncertainty of these cosmic mysteries. Black holes will continue their ancient dance through space and time, neither purely destructive nor simply transformative, but something more subtle and beautiful than either characterization can capture. In their darkness, they hold light. In their finality, they enable new beginnings. In their simplicity, they encode infinite complexity. They are the universe's greatest teachers, offering lessons in physics, philosophy, and the profound interconnectedness of all things. Sweet dreams, fellow traveler. May your journey through sleep's mysterious realm be as peaceful and transformative as the cosmic dance we've shared tonight.